When we talk about the great geopolitical semiconductor war of the 21st century, we always think of the bitter multi-trillion-dollar standoff between the United States and the People's Republic of China. Our brains instinctively picture physical objects because these objects are tangible, because we can touch them, measure them, and load them onto massive cargo ships crossing the Pacific Ocean. They have naturally become the default metric by which the entire world measures progress. The prevailing assumption in Washington, in Beijing, and on Wall Street is fundamentally based on simple mathematics. If the Chinese state simply allocates enough capital, builds enough factories, and hires enough brilliant engineers, domestic tech firms will eventually reverse engineer an artificial intelligence chip that perfectly matches the physical specifications of an American NVIDIA GPU. If you listen to Chinese state media, or even certain prominent tech executives in Silicon Valley, the narrative heavily suggests that this hardware gap is already closing. Armed with an essentially unlimited blank check of state subsidies and a captive domestic market barred from buying top-tier American technology, China's grand strategy seems brutally straightforward. Design a comparable chip, manufacture it domestically, and break the American monopoly. And here's the crazy part. On paper, they are actually doing it. Companies like Huawei have successfully designed domestic AI accelerators, most notably the Ascend 9 Wannabe and the newer Ascend 9 One OS. If you look at the spec sheet, these pieces of silicon boast raw mathematical capabilities that genuinely approach NVIDIA's older flagship models. But there is a fatal multi-trillion-dollar flaw in this logic. We are looking at the wrong battlefield. Silicon, at its absolute core, is merely highly refined sand and trace metals. It is a rock that human beings have tricked into doing math, an artificial intelligence accelerator. No matter how physically advanced, is entirely and spectacularly useless. If the world's developers lack the software libraries, translation layers, and communication protocols required to actually instruct it, while politicians and policymakers spend vast amounts of time and energy obsessing over physical hardware bands, export controls, and microscopic transistor sizes. The true reason the Chinese semiconductor industry cannot simply copy NVIDIA is something entirely invisible. The insurmountable barrier isn't the physical silicon being printed in those massive Taiwanese factories. It is a software platform, a networking monopoly, and a developer ecosystem that NVIDIA has been quietly building, perfecting, and embedding into the global technological subconscious for the last 2 decades. To comprehend the terrifying scale of the challenge facing China today, we first have to look at the physical reality of the silicon itself. In October 2022, the United States Department of Commerce initiated unprecedented sweeping export controls. Overnight, Chinese tech giants were abruptly and violently cut off from the global supply chain of advanced semiconductors. In response to this existential threat, Huawei emerged as the nation's primary champion, tasked by Beijing with the monumental burden of filling the massive void left by NVIDIA. By 2024, Huawei had answered the call. They introduced the Ascend 9 One OBE and shortly thereafter, the 9 One OS. Make no mistake, on a pure hardware specification sheet, the 9 One CE is an absolute marvel of engineering. It was explicitly designed to compete with NVIDIA's Hopper architecture. Chinese internet and telecommunication giants desperately needed computing power. By late 2024, they reportedly placed orders for at least 70,000 units of the 9 One AOC, representing an investment valued at roughly $2 billion. At approximately $28,000 per chip, Huawei was commanding prices virtually identical to what NVIDIA historically charged for its flagship H1. But here is the foundational lore of the global semiconductor industry. Designing a brilliant theoretical chip on a computer screen is one thing. Actually, manufacturing millions of them perfectly at a microscopic scale is an entirely different universe of physics. NVIDIA doesn't actually manufacture its own silicon. They are what the industry calls a fabulous company. They just draw the blueprints to build the physical chips. They hand those blueprints over to TSMC in Taiwan to print microscopic circuits at the 4 nanometer and 3 nanometer scale. TSMC utilizes extreme ultraviolet or EUV lithography machines. These machines are arguably the most complex devices ever built by human hands. They are manufactured exclusively by a single Dutch monopoly called ASML to create the ultra-fine light needed to print these chips. The machine shoots a high-powered industrial laser at a microscopic droplet of molten tin 50,000 times a second, vaporizing it into a glowing plasma. Because of stringent international export controls orchestrated by Washington, Chinese foundries are legally prohibited from ever buying these EUV machines. So Huawei is forced to partner with domestic foundries, primarily the Semiconductor Manufacturing International Corporation, or SMIC. SI has to rely on older, deeply inferior equipment called deep ultraviolet or DUV lithography to try and achieve modern 7 nanometer and 5 nanometer transistor densities using older DUVHA machines. SMISI uses an agonizing technique called multi-patterning because their marker is too thick to draw the microscopic lines. They essentially run the silicon wafers through the older machines 3, 4, or even 5 times. They try to etch finer and finer lines by overlapping them, hoping the negative space creates the ultra-thin circuit they need. It is an engineering workaround of epic proportions, but it is an absolute economic disaster. Every single time you run the wafer through the machine again, the chance for a microscopic misalignment increases. And at the atomic scale, a misalignment of a fraction of a nanometer means the circuits cross the chip shorts out and it becomes a highly expensive piece of garbage. The data supporting this comparison is stark. By early 2025, industry reports indicated that the manufacturing yield for the Huawei Ascend 9100C had reached approximately 40%. That means for every 10 incredibly expensive chips SMIC prints, 6 are defective and have to be literally thrown in the garbage. While this marked the first time the Ascend production line was considered even marginally profitable, and Huawei aggressively aims to push this yield to 60%. It remains a fraction of TSMC's 90+% flawless efficiency. The final production costs for IC are up to 50% higher than what NVIDIA pays TSMC because of this brutal manufacturing bottleneck. US intelligence officials estimated Huawei could only physically produce a few 100,000 advanced AI chips throughout 2025. Is that enough to keep Chinese priority national security projects and military research afloat? Yes, but it is a drop in the ocean compared to India's global shipments scale, which measures in the millions. NVIDIA's manufacturing economics are pristine by operating at massive scale with TSMC. The physical manufacturing cost of an NVIDIA H100 accelerator is estimated at roughly $3,320. When you sell that piece of metal to a data center at market rates nearing $28,000 in video commands, an astonishing, almost unheard of 88% gross margin. This physical hardware deficit alone is severe. But as we are about to see, the foundries are just a distraction. The real war isn't happening in the physical factories. It's happening in the code to understand the deepest, most treacherous part of NVIDIA's invisible moat. We have to travel back in time, not to last year or to the start of the AI boom, but 20 years ago to the year 2006. In 26 graphics processing units, or GPUs, were highly specialized niche hardware components. They were designed to do one thing and one thing only: render polygons for video games as fast as possible. But NVIDIA's founder Jensen Huang had a radical world-changing realization: a standard computer CPU is like a race car. It's incredibly powerful, but it processes logic sequentially. A GPU, however, is built differently. It contains thousands of tiny, highly efficient cores. Huang realized that if you could harness those thousands of cores, you could perform incredibly complex general-purpose mathematical equations simultaneously. This is called parallel computing. It could theoretically be used for simulating weather patterns, mapping the human genome, or eventually training artificial intelligence. There was just one massive glaring barrier programming a GPU. To do anything other than render a video game was an absolute logistical nightmare. You had to trick the graphics hardware into doing math by writing code using obscure, deeply complex graphics languages that no traditional computer scientist wanted to touch. To solve this, NVIDIA created a software platform called CUDA, the Compute Unified Device Architecture. CUDA acted as a universal translation layer. It allowed normal developers to easily write code for NVIDIA GPUs using standard everyday programming languages like C++ or Python. When Jensen Huang launched CUDA, Wall Street absolutely hated it. Investors were furious. NVIDIA was spending hundreds of millions of dollars and artificially increasing the manufacturing cost of every single gaming chip they made to include a software layer for a scientific market that literally did not exist yet. Jensen famously called it investing deeply in a $0 billion market. NVIDIA's stock price cratered, but in video, it didn't blink. Over the next decade, while their competitors slept, NVIDIA aggressively seeded CUDA into universities, research laboratories, and enterprise startups worldwide. They essentially gave the foundational language of parallel computing away for free. So when the artificial intelligence boom finally ignited in 2012, sparked by researchers using the ALEX-CNET neural network to instantly recognize images and crush the competition, how did those researchers achieve their breakthrough? They used CUDA by establishing their software foundation years before the race even began. NVIDIA ensured that as the AI industry grew from its infancy, it grew entirely within the borders of the NVIDIA ecosystem. Today, nearly every major artificial intelligence framework on the planet, from Meter's PyTorch to Google's TensorFlow and JAX, is fundamentally optimized to run natively on CUDA. It is the English language of artificial intelligence. Over the last 2 decades, NVIDIA has continuously refined a vast library of highly optimized, pre-written code for deep learning like SIU-DNN, which accelerates neural networks, and TensorArt, which optimizes how models make real-time predictions. This is the ultimate unbreakable network effect. Developers only learn and write code for NVIDIA because NVIDIA hardware is ubiquitous, and trillion-dollar tech giants only buy NVIDIA hardware because it is the only architecture. The global talent pool actually knows how to utilize efficiently. The correlation is staggering. In 2021, NVIDIA reported approximately 2.5 million developers utilizing its platforms, which correlated to roughly $10 billion in data center revenue by 2024. That developer base had more than doubled to 5.1 million, driving data center revenue to $47.5 billion by the fiscal year ending January 20th, 2026. NVIDIA's data center revenue had surged past $115 billion annually, and this is precisely why China cannot simply clone the physical chip. If a Chinese semiconductor firm miraculously designs a piece of silicon that is equally as fast as NVIDIA's equivalent, that raw speed is completely irrelevant. If the chip does not natively speak CUDA, an AI researcher would be forced to rewrite years of complex code, manually translate low-level math primitives, and forfeit the stability of an 18-year-old ecosystem just to turn the new Chinese hardware on. Chinese tech giants are painfully aware of this massive software deficit. Huawei has spent years frantically developing its own equivalent software stack called Can Compute Architecture for Neural Networks, alongside a PyTorch plugin designed to help developers port their existing models over to Ascend chips. But matching the rich documentation, the rock-solid stability, and the massive third-party library support of an 18-year-old ecosystem is proving nearly impossible. Researchers testing domestic Chinese chips frequently report severe project-killing stability issues when random errors occur during the training of massive AI models, which cost millions of dollars in electricity and compute time alone. Developers using Huawei's can often struggle to pinpoint the origin of the fault because the software documentation is incredibly poor, according to industry insiders. It is so bad that Huawei has literally been forced to deploy its own highly paid engineers directly to customer data centers, flying them across the country just to sit over their clients' shoulders and manually rewrite their computer code into CAN. Desperate to bridge this terrifying gap, some developers attempted to use translation layers, software tools like zLoader or Scale, which act like a live Google Translate, theoretically allowing Q to compiled software to track non-inferior hardware, including Chinese GPUs, into running it. But NVIDIA was watching, recognizing this as an existential threat to their invisible moat in video dispatch. Their armies of corporate lawyers. They swiftly updated their software licensing agreements to explicitly ban the use of translation layers to run computer code on competing hardware. It is now a literal breach of contract. The invisible moat is actively defended by corporate lawyers just as fiercely as it is by software engineers. And this CUDA monopoly is the true anchor of NVIDIA's $4.4 trillion valuation. Okay. Let's play devil's advocate for a moment. Let's pretend the Chinese state-backed company somehow solves the manufacturing yield problem with SAM. I see. Let's pretend they miraculously write a software platform from scratch that rivals CUDA, and they successfully retrain 1 million developers to use it. They are in the clear, right? Wrong. because they would immediately smash headfirst into a second brutal physical reality of the modern era data center. Networking frontier. AI models are no longer trained on a single computer chip. They are simply too massive. The training of a state-of-the-art large language model requires clusters of 10,000, 20,000, or even 100,000 GPUs operating simultaneously in absolute flawless synchronization. At this terrifying scale, the engineering bottleneck shifts entirely. The primary constraint is no longer how fast a single chip can do math. The constraint becomes how fast tens of thousands of chips can communicate with each other without stalling, crashing, or waiting in line for data. If a $30,000 piece of silicon spends 40% of its time sitting completely idle, waiting for a data packet from a chip across the room, you are burning millions of dollars in wasted electricity and time, recognizing years in advance that the future of computing was moving from single processors to data center scale infrastructure, NVIDIA executed a strategic masterstroke. In 2019, for $7 billion, they acquired Mellanox Technologies, an Israeli-American supplier of ultra-high-performance computer networking gear. This vital acquisition gave NVIDIA total absolute control over a technology called InfiniBand, an industry-standard networking protocol designed specifically for zero-latency server-to-server communication. Furthermore, NVIDIA spent billions developing its own proprietary physical interconnect cables called NVLink. Traditional computer motherboards are too slow, and the link allows GPUs within the same server rack to bypass the motherboard entirely and share memory directly at blistering, incomprehensible speeds. To manage this hyper-complex choreography of data movement, NVIDIA utilizes another proprietary software layer called NCCL, the NVIDIA Collective Communication Library. NVIDIA effectively no longer sells individual chips, they sell entire prepackaged supercomputing infrastructures. They control the switches, the optical cables, the data processing units, and the sophisticated software that routes the traffic. For Chinese manufacturers attempting to replicate this networking symphony is perilous because the single-chip performance of Huawei's Ascend 9.1 OS naturally lags behind NVIDIA's latest architectures. Huawei is forced to rely heavily on scaling horizontally. They attempt to weave an all-to-all topology using their own unified bus interconnect technology, fundamentally trying to brute force thousands of weaker chips into acting as one cohesive cluster to match a smaller-end video system. But this brute force approach comes with severe, painful penalties. Chinese industry insiders and researchers frequently cite slower into-chip connectivity and staggering power consumption as massive hurdles. Huawei's Cloud Matrix cluster, for example, is reported to consume nearly 3.9 times more power than an equivalent NVIDIA GB200 system to perform similar workloads. When you try to synchronize massive clusters of Huawei silicon for an initial model training run, the sheer volume of network traffic combined with the instability of the CAN's software stack frequently leads to catastrophic system crashes. The supercomputer symphony breaks down into noise. The technological barriers of software and optical networking are massive enough on their own to protect NVIDIA's monopoly, but they do not exist in a vacuum. They are currently being crushed by the volatile geopolitical reality of the 2020s. The United States government views artificial intelligence not just as a lucrative commercial tool, but as a critical generation-defining national security domain. And Washington has systematically weaponized its absolute control over the global semiconductor supply chain to ensure China remains a generation behind. Starting in October 2022 and expanding ruthlessly through 2023 and 2024, the Biden administration implemented unprecedented restrictions aimed at choking off China's access to advanced AI chips. This physical chokehold resulted in a bizarre, highly reactive dynamic that ultimately proved just how powerful NVIDIA's invisible software moat truly is. In response to the initial export controls, NVIDIA designed the H20 chip specifically for the Chinese market. The H20 was intentionally degraded, its computing performance was surgically throttled to remain just legally below the US regulatory threshold, allowing NVIDIA to continue servicing its massive Chinese clientele. Legally, logically, one might assume that Chinese companies faced with the option of buying intentionally crippled American chips or heavily subsidized domestic Huawei chips would choose their national champion. They didn't. Despite the severely degraded performance, Chinese entities like ByteDance, Alibaba, and Tencent rushed to stockpile the crippled NVIDIA hardware in 2024 alone. They spent an estimated $16 billion to acquire over 1.3 million H2O units before further bans could be enacted. The desire to remain within the safety of the computer software and NVLink networking ecosystem was so fiercely strong that Chinese tech giants willingly purchased objectively inferior hardware rather than face the sheer terror of migrating entirely to domestic alternatives. Furthermore, US policymakers began to realize that the total embargo on advanced chips was inadvertently backfiring. It was acting as a massive subsidy for SMB, C, and Huawei, rapidly accelerating China's drive for true technological independence by allowing the highly capable H to go back into China. The US theoretically maintains American technological market share, cashes in on billions in revenue, and simultaneously dampens the momentum of Huawei's domestic hardware adoption. To truly grasp why China's locally sized isolated attempts to clone NVIDIA are faltering, you have to zoom out. You have to look at the sheer planetary scale of NVIDIA's global infrastructure rollout currently happening right now. In April 2026, while Huawei is fighting tooth and nail to painstakingly manufacture a few 100,000 chips at a 40% yield using restricted DUV lithography machines, NVIDIA is no longer just shipping chips. They are orchestrating the construction of gigawatts-scale AI factories around the globe with the introduction of the Blackwell architecture. NVIDIA fundamentally shifted the entire computing industry. The flagship product is no longer a discrete piece of silicon. You plug into a motherboard. The flagship product is rack-scale computing. Meet the gigabits per second 200 NVIDIA XL72. This is a single liquid-cooled, multi-million-dollar server rack weighing thousands of pounds connected by a sprawling 130 terabyte per second copper backplane. This entire rack operates logically to the software as one single massive superchip by operating at this rack scale. NVIDIA completely minimizes the inherent latency inefficiencies of networking individual servers together entirely. This architecture delivers up to 30 times faster real-time inference 4 trillion parameter AI models compared to the previous H1 generation, and it operates at 25 times the energy efficiency. And this level of integrated hardware, orchestration, is being deployed globally at a pace never before seen in human history. Let me know your thoughts in the comments below, and make sure to subscribe for our next interesting video coming soon. This is Kyle, and you are watching Beyond Economy.